Okay, let's go ahead and start. This is the last week of lecture, and next week we're gonna have one more lecture, and then it will be the final exam. So, very close to summer. Okay, hooray! And gentle reminder, what's being due this Friday are 4 quizzes, I think, 29 to 33. And all the PAs are done, so great. Just the quizzes. And there are going to be two topics today. The first is distance vector routing. Okay, so let's go over the example again, and you'll be going through a quiz number 34. And then we'll begin to discuss the remaining issues about the distance vector routing. And then there's going to be another quiz coming up. Okay, so let's go over the example again. Oh, and by the way, what I'm going to do today is, oh, hi, Rocket. Hi, Jiazi. Yeah, so I'm just gonna, review going through the slides live. Okay. So, real quick, okay, distance vector works this way. It's gonna be continuum with lots of iterations of the same thing again and again. So first is to wait, and if there's a link cost change, or receiving a distance vector from a neighbor, then it triggers the Bellman-4 equation being recomputed. And the result is having the new distance vector. Now, in case there's any change in the distance vector, we send the distance vector to the neighbors again. Okay, so very simple. Getting updates, okay, either from the neighbors or detecting a link cost. Recompute Bellman-4, send the new distance vector to the neighbors. And so last week, towards the end, we actually went through an example, right? So in the example, we define how we initialize the distance vector. So this is no-ace distance vector table that contains the distance vector that x will need to calculate all the time. And then it contains also the distance vector from the neighbors. Now, in this example here, x is over here, okay? And it's going to receive distance vector from y and z, these two neighbors. So dv is going to be stored here, dz is going to be stored here. Okay. Similarly for y's table, this is the one that y needs to calculate, and these are the two receiving from the neighbors. Now, let's talk about initializing dx for no x. Okay, and the process is similar for initializing dy for no y. Okay. So, again, very simple. X is right here. To initialize dx, set all the values to infinite. Okay, so there could be more destinations up here. All the values are infinite. Okay, but reset the value to itself. So x to x itself, trivial, cost is 0. X to immediate neighbor, y to immediate neighbor, z. Yeah, the distance, let's set it to the link cost to the neighbors. So we see, therefore, 2 and 7 here. And for all the other nodes in the network that is not directly adjacent to the node here, set them to infinite. And for the vectors we have not yet received from the neighbors, set them all to infinite as well. So that's why you see the x being 0 to 7, dy similarly, right? So y here to the two neighbors, cost is 2 and 1, therefore you see 2 and 1 here. Cost to itself, 0, and all the other entries, infinite. Now for a very simple network, having only 3 nodes, we have only 3 columns, okay, in the table. Now, we may begin to work on the first iteration, because once dx is initialized, it's going to be distributed to the neighbors. Okay, this is the new distance vector. Y here, updating the dy, it's going to also send the distance vector, okay, to the neighbors. Similarly, z sends the new distance vector to the neighbors. As a result, no x here, okay, is going to update dy from the distance vector coming from no y, dz from the distance vector coming from no z. Now, dx here, okay, receiving distance vectors from neighbors, will trigger calculation of the Bellman-4s. Therefore, we'll need to recalculate dx again. What I meant that is simply to calculate this value and this value. So that is xy and dxz. Now, to calculate dxy, recall the Bellman-Ford equation. So it's actually to try to find out the shortest distance from the source to the destination. Source to the destination. Now, this is source x to destination y. So source x to destination y. Now we'll be trying through all the neighbors. So who are x's neighbors? Y and z. So we have two entries here, one and the other one. First neighbor y, second neighbor z. So let's walk through the first item. So again, from x to y, that is the goal. And let's go through neighbor y. Now, according to the Bellman-Ford equation, okay, the value that is first is the link cost from x to the neighbor y. And that is 2. And then consider the shortest distance from the neighbor to the final destination. Okay, so the neighbor is y and the destination is y itself. And this value here, okay, dy y will have to look up the table because that's y's perspective. So in y's perspective, the shortest distance to y here, the value is 0. Now we do the same for the other neighbor. Again, x to y, okay, and going through neighbor z. And so what do we do there? Yeah, according to the Bellman-Ford equation, first is to take the link cost from the source to the neighbor. And then from z's perspective, what is the shortest distance to the destination y? So this is 7. And from z to y, that will depend on what dz says. So from z to y, value is 1. Okay, so in the end, we ended up having 2 being compared to 8, and we picked this one here. So y here, okay, is the neighbor for the path to go from x to y. So we fill in this value, okay, to dxy. Similarly, we calculate dxz. So that is for source being x and destination being z. What is the shortest distance that we could see now? So from x to z. X to z. Now let's try the first neighbor y. Link cost from the source to the neighbor 2. And the shortest distance from the neighbor to the destination. So that will be dyz. And dyz is, according to dy there in the table, it's 1. Similarly, from x to z, but going through the second neighbor, z. Link cost being 7, and then dzz being 0. So 7 plus 0. 3 versus 7. 3 wings. Therefore, we fill in the entry here. Okay, so this is how you develop dx for no x. And that also takes us to the first quiz today. See, let me bring up the quiz real quick. It's right here. So the quiz is actually asking you to use the same example, okay, that we just used. And this time, to develop the distance vector for no z here, okay, at time t1. Okay, let me explain what's time t1. So what we were doing earlier for no x here is the distance vector at t1. So all I'm asking you to do for quiz 34 is just to develop, okay, dz for no z here. Okay. And so I'm already filling in the row of dx and dy, assuming that, no x and no y already sent their initial vector. Okay. So can you calculate dzx and dzy, okay, for quiz 34? Okay, so yeah, this one should be relatively easy, but it might take a while. So why don't we give it a good 5 minutes of time so you guys have time to exercise? Okay, just go back to the OBS and then, so this is what you guys are asked to do. Okay, too fast. Okay. Okay, so maybe we should cut it to 3 minutes. So we do have team 1 and team 4. Okay. Submitting a solution. Oh, wow. Okay, so that seems to be unexpectedly simple for you guys, which is a good thing. 13 and 5. Okay. All right, so I see Ji Ting, Pei An, Wei Cheng. Yeah, oh, Hao Yu as well. Okay, and RNG, good morning. All right, good. So that was too easy, I guess. Yeah, so why don't we come back here and see if we could complete, okay? And walk through dz here, okay? And then complete the entire, okay, derivation, okay, of the distance vector until the whole system converges. How about that? Okay, so dz, essentially we calculate zx, okay, and zy. So zx is what? From z to x, z to x, okay? And checking out the two neighbors, x and y, what is the shortest path? Okay, so z to x, link cost 7, and then dxx 0, so 7, 0, so xx 0. From z to x through y, on the other hand, link cost, zy being 1, and then yx, so yx value 2. There. We get 3 here for dzx, and that is 3 right here. Similarly for dzy, okay, let's remove the markup, z to y. Okay, there are two neighbors, x and y, link cost 7, x to y, 2. So 7 and 2. For the second neighbor, okay, so we're still trying to go from z to x, second neighbor y, link cost y, link cost xy being 1, and then y there, dyy there, 0. So 1 and 0. So 1 here wins, and therefore we get 3, 1, 0. Perfect. You guys are all correct. Now, have you guys tried to develop dy for node 2? Some of you probably did. Okay. This one is also very straightforward. Y to x, drawing through neighbor x, so link cost 2, and then dxx, link cost 2, dxx 0. Similarly, y to x, but going through neighbor z, link cost y, and then dzx, 7. So 1. Wait. Something's wrong here. Z to x 7. Yeah, z to x 7. But link cost 1. Okay, good. So I was not mistaken. And therefore, comparing 2 to 8, we get 2. Okay, so similarly, we fill in the last entry. I think by now you guys all get a hang of it already. Very good. Now, the only remaining bit to talk about is just this. Look at this. Hey, 201, there's no change. Okay, 023, 027. Oh, there's change here. Now, no x here after deriving dx, which is different, having a change, needs to send the distance vector to both the neighbors, which includes y and z. Similarly, when z come up with 310, which is different, Z here will send to also X and Y. But no Y here, not seeing a change in the distance vector, will not do any transmission. Okay? So that is actually what I was trying to talk about in the last bit of the video last week. You see here? Okay, this is the same example. Okay. 0, 2, 3 is different from 0, 2, 7. Therefore, new distance vector gets delivered to neighbor Y and neighbor Z. And therefore, we see this row here change from 0, 2, 7 to 0, 2, 3. Similarly, in Z's table, okay, we change that to 0, 2, 3. Okay, so these neighbors distance vectors gets updated. Okay, as soon as Y and Z receive the change, they're gonna trigger recalculation of the Bellman-4 equation again. It's just that in this second iteration, T2 here, hey, there's no change here, no change here. Therefore, Y will not change dz any further. Z will not deliver dz any further. Okay. Similarly, when this is changed, it's gonna. Similarly, when Z's dz gets changed, this is gonna be sent to X and Y. So we see here, okay, it gets changed to 310. This gets changed to 310. Okay, and with these two received, dy triggers, y triggers dy being recalculated, x triggers dx being calculated. Okay, again, no change, no change. Okay, x will also stop forwarding from here. Okay. But this guy here, okay, the dy did not change. Therefore, there's no forwarding of dy starting from the first cycle. And so in the end, you see in one cycle and two cycle, or in one iteration, two iteration, okay, the route converges to the optimum. Okay, so this is distance vector. Okay, you see it's very iterative and somewhat asynchronous. Okay, whenever there's a link change, we update and update based on the Bellman-4 equation. Whenever there's a message received, we also update, and again, based on the Bellman-4 equation. So that was example number 1. And that is the topic, the first topic today. Oh wait, we do have, is the screen not switched? Sorry. So did I just talk to myself? Yes, I did. Okay, so that was the problem, why I decided to just play video. Okay, so yeah, let's just quickly go over. And let's not go over the entire development of the table for solution, for quiz solution 34. Okay, so what I was just going through was just this. Okay, wait. What I was just going through. Excuse me. And just make sure that I got switched to this. So what I was just going through is just to calculate 310, which you guys all did. And some of you guys might try to calculate dy for no y. And that quickly, just do the Bellman-4 equation again. We should get 2 and 1. Therefore, we'll fill in this entry. And what we can observe in quiz 34 is this. Dy did not get changed, while dx gets changed and dz gets changed. And that was the last bit I was trying to talk about in the video. The last video last week. Right here. So dx gets changed. Therefore, it delivers dx to no y here and no z here. So no y's x entry, no z's x entry, you see they get updated. Right? And at this point, no y is going to trigger dy being recalculated. No z is going to be triggered to get dz recalculated. Similarly, when z updates dz, that is a new entry, because it's different from 710 previously. So x and y here would both update the DZ entry. Okay? And again, no y will recalculate dy, no x will recalculate dx. It's just that in the second iteration, okay, all these, okay, remain the same. No more changes, therefore no x, no y, no z. Okay, none of them distribute the distance vector any further. And so right at this point here, T2, after one iteration, two iteration, we converge to the shortest path for all the nodes to every other node, right? And you see here, particularly dy was originally initialized to 201, but after the first calculation of dy, you see immediately, okay, after one iteration, dy converges already. There's no more message exchange from node y to the neighbors. So potentially the amount of message exchange, okay, is actually less than those we see in the link state report, which must flood through the network. Okay, so this is one of the advantages of distance vector. Okay, lower number of these messages we need to pass around. And you see in this example, which is very simple, it takes only two iterations and then we converge. But for bigger network, typically networks with longer diameters, meaning, okay, the longest distance to take from one node to another. For longer diameter networks, the longer number of iterations to converge to the shortest path. So that was the first example. I hope that is more clear. And now we move to the second topic.
Let's try to calculate the distance vector of z.
Oh, wait. Sorry. Let's move to the second topic, which is the discussion of the distance vector routing. Okay? We do see an issue with distance vector routing. Okay? That happens when we update the distance vector such that, okay, the path goes wrong. Okay? And this happens all the time when we do a link cost change. Consider cases where you use, for example, congestion level, okay, or traffic amount going on a link as the link cost. Okay? So when we have more traffic going on, then the link cost goes really bad. Okay? So in such a case, we do have a trouble with the distance vector. Let's go over it and talk about when there's link cost change, what's going to happen. So one very interesting property with the distance vector routing is this. Whenever there's a good news in the network, it travels really fast. Okay, so when there's a better route, it gets propagated really fast and everyone converges really fast. But if it's bad news, meaning if a route suddenly goes bad, okay, it will take a long time for everyone to discover, okay, the route is really bad and we should really be going another way. Okay, so let me describe the first case, the good news travel fast case. So recall. Okay, this is the change where the link between x and y is reduced from 4 to 1, so good news. The node is going to detect local link cost change and update the routing information and trigger Bellman Ford. If the distance vector changes, then send to the neighbors. So here, link change from 4 to 1. So at time 0, y is going to detect the link cost change and update its DV and inform the neighbors here and here. So next point in time, z here, is going to receive this distance vector from y. Okay, it's going to see, oh, the shortest distance from y to x is now 1. Okay, therefore z is going to update the shortest distance to what? 1 plus the cost from going from y to x, which is 1 now, that is 2, which is better. Okay, so z is going to update its own dB and send it out to the neighbors. And y is going to receive z's update. Okay? Z says, okay, the shortest distance to x from me is 2. And y sees that, hey, I do have a direct connection. My shortest distance is already 1, right? Your shortest distance to x is 2, plus the link cost from y to z. This path is not better. Okay, so y there will not discover a new path, okay, a better path to x. Therefore, distance vectors stay the same, okay, no more message being sent out, okay, back to z. Network converges. Everyone goes to the steady state. The second case is the bad news travels slow. So you see from the scenario, the link cost, instead of dropping to 1, now goes up to 60. Super bad news. Of course, x and y here would detect there's a link cost change. But in this scenario, it would take us 44 cycles until the network goes back to the steady state, until they all converge to valid shortest path. Okay. Now, bad news travel slow, meaning routes converging slowly. Okay, that is also referred to as the count to infinity problem. Now let's go to a quiz to see what's going on there. Okay. And here's the quiz. So number 35 here is exactly to exercise how bad news can go slow. Okay, so all you need to do is just to answer quiz Q1 here. Okay, to develop x and y's table right after the change. Okay, so it's the same scenario we see in the slide. So essentially what I'm asking you to do is this. Okay, the first column to the left. Okay, so these are the table of x and y and z before the link cost change. Okay, so right at the link cost change, okay, dx in no x there, okay, needs to be changed. So let me again go to the slide here. So essentially, yeah, no x here. Right after link, yeah, dx is going to be recalculated. So what I'm asking you in Q1 here is to try to calculate, yeah, for dx, okay, what will be the values right after the change. Similarly, no y, yeah, after detecting the link cost, y is going to recalculate the dy, and what are the values here? All right, so yeah, we need to calculate for 4 values, so that's spend some 7 minutes of time on it. Okay, so dy and dx, dy for no y and dx for no x. Wow. David, good job. Very good job. Yeah, but let me just share that it's a little bit tricky though. Yeah, it's a little bit tricky. Okay, Jiazi also come up with the same thing. ING also. Silvercraft. So do you all come up with the same thing? It's actually a bit tricky this time. So any other solutions? Okay, very good question, Jiazi. So if you are know y, all you know is from y, the link cost to the neighbors, and then dx and dz, and that's all. You actually don't know there's a link between x and z, the cost is 50. If you are know y, you see. Yeah, because we are all human beings, we kind of see the whole graph. Okay, and so we tend to think like link state. Okay, knowing the whole topology, you know immediately what is the shortest path from y to x, right? Which is 1 plus 50. Shortest path to z, obviously y to z. But if we follow the distance vector algorithm, okay, well, it actually is going to look different. Yeah. So yeah, why don't Polly show how she developed dy and dx in the t0 cycle? I think you guys got it. But let me walk through the video so that it's very clear to you. So one very interesting property with the distance vector routing is this: whenever there's a good news in the network, it travels
sorry.
really fast.
Yeah,
Yeah,
quiz
wrong
35, the
video.
scenario is a bit tricky. Let's try to be patient and walk through the derivation of dx for no x and dy for no y. Let's start from dx. Let me just show the final result real quick. Yeah, the xy here, the first value should be 51. The xz, the second value here, should be 50. Okay, and the detail is this, again, from the source to the destination. So dxy, the source is x, destination is y. Through two neighbors of x of the source, that will be y and z. So we have y and z here. So link xy costs 60. Link xz costs 50. So we do have 60 and 50 here correspondingly. And then through first neighbor y, what is the perspective? What is the shortest distance to the destination? Well, y to y, we'll have to look up the table coming from no y in order to find out, right? That is y's perspective. So that's in dy coming, came from no y earlier. So dy y, then it's 0. And then, yeah, for the second neighbor, z, what is z's perspective, the shortest distance to y? That will be what? dz to y. So dz to y. And that is in distance vector of z came from no z earlier. Z to y, yeah, it says 1. So we put 1 here. So sum of trying through neighbor x, 60. sum of trying through neighbor z, 51. Therefore, no z here, wings, and the shortest distance is 51. Similarly, we derive dxz from x to z. So clear the markup from x to destination z. There are two neighbors again, y and z. X to the first neighbor y costs 60. X to the second neighbor z, link costs 50. So again, 60 here, 50 here. And then from y, what is the shortest distance to z? Shortest distance from y to z, that would be y to z being 1. And then the second neighbor, z's perspective to go from z to z. Shortest distance from z to z, z to z, 0 here. 61 compared to 50, so we pick 50 as the shortest distance from x to z. Now, it's not so bad. Okay, let's derive next. dy. Okay, again, let me put up the solution first. So dyx, the first entry here, you thought, right, it should be 60, obviously, but this is, hey, as a human, you see the global topology, you know it's 60, but distance vector is actually what? Making decision based on local information, based on information provided by the neighbors. So let's be careful, and then still walk through the Bellman-4 equation. Okay, so dyx, source being y, destination being x. Going through two neighbors, x and z. Link cost is link cost yx is 60. Link cost yz is 1. So we have 60 here and 1 here. Now going through neighbor x, what is the shortest distance to x? dxx, we'll have to look up the table. dxx, which is 0. Going through neighbor z here. What is the shortest distance from z to x? Z to x. That will be looking up the dz vector, okay, and going to x. So it's this guy here, 5. So we put 5 here. And you know what? Bellman-4 equation says comparing 60 to 6, 6 wings. Okay, and that is actually going through no z. So y is going to pick. Okay, saying to go to x, let me send it to z first, and then z says I know a way to x, which is, yeah, the old impression, right? This way. So you see the packet there is going to go y to z, z to y, but y is going to say that, hey, to go to x, you need to borrow z, okay, as the middle point. So that packet is going to loop around between y and z for a while. Interesting, isn't it? Yeah, this is actually a very interesting characteristic of distance vector. Okay, before the route actually converges, the packets could potentially be in a routing loop. So 6 here, again, is the new dyx. Okay, it's not quite yet the true, okay, dyx. Okay, so you see here, even though y is capable of detecting, there's a link cost change right here. Okay, but y's routing decision, route calculation, is still based on the ODX and ODZ. Okay, and right at the link cost change, no y, okay, have not yet received the new DZ, new DX yet. So y is going to be using the ODZ and ODX. Therefore, you see, okay, the ODZ is telling y the shortest distance from z to x is 5 here. So we will be, in the short term, okay, under the false impression that this is the best route. Y sent to z, okay, and z will somehow know a way. The cost is only 5 to x. You should get a sense that it's going to take a while for these routes to converge to the shortest path. As to how long, yeah, let's try to walk through the scenario for a couple more iterations to see. So we'll develop the table, okay, for T1 and T2. Okay? And at T1, Z here can try to calculate dz because it now receives the distance vector of dx and dy coming from no x and no y correspondingly. And so dz here contains two entries, dzx and dzy. Now let's ignore the calculation of dzy as this one is very trivial and we know how to do Bellman-Ford equation already. Let's go over, however, dzx carefully because this entry here is very interesting. So once again, okay, from source z to destination x, two possible neighbors of z, x and y. So first neighbor here, the link costs 50. Second neighbor here, link costs 1. So we have 50 and 1. And then the final destination is x, so we need to know the value of dxx. Final destination is x, so we need to know dyx. So for these two entries, we do table lookup because this is actually x's perspective. Okay, so this is what x has informed z. So what x has informed z is the dx. So in x vector, okay, to destination x, entry will be 0. In y vector, for destination x, entry value 6. So 50 compared to 7, 7 weeks. And therefore, we update dz to 7, 1. Now, what's interesting is this. Z thought, okay, the shortest path to x is now what? 7. And the best neighbor is z. So z thought, okay, next hop to forward the packet, destination being x, should be y. But you see, y here thought, okay, the shortest distance to x is 6, and the next hop is z. Yeah, because z knows a way, okay, much earlier saying, oh, the shortest path to x is 5 and next hop is z. Okay. So you see we have actually looped it 1.5 times, okay, on link y and z trying to develop, okay, what is the true shortest path. If we continue on, okay, as z here finished calculating dz, this is going to go out and reach no y and no x. As a result, no y here can calculate dy again, provided the new dz. Let me bring up the result. dyx, this value here, is gonna be 8. Let's look through it again. Okay, from y to x, y to destination x, through neighbor x, neighbor z. Link cost 60, link cost 1. Link cost 60, link cost 1. dxx, 0. dzx, look up the table. Z's x, 7. 7 here. So, wow, we get A. What does that mean? Yeah, although we update the table for y so that it's 8, 0, 1. But you see, y here, actually believe firmly z is the best neighbor to forward the packet because z knows a way which takes only 7, okay, dollars to go to x. And this is going to go on, in fact, because y here is going to announce dy also, okay, to all the neighbors. And z is going to recalculate the dz. And guess what? The next is going to be 9, 1, 0. And back to y, 10, 0, 1. Okay, all the way until when? Until z finally discovered that 50 is the true cost to x. So until, okay, in dz, the value becomes 50, 1, 0. Okay. And how many iterations would that be? Yeah, I came all the way from 7 to 50. That will be 43 iteration. Okay. And including the initial iteration, that will be what? 44 iteration. Okay. Until Z discovered the true path. Next, then Y will discover the true path. And then everyone converge to the shortest paths that are really true.
The problem here is, okay, right after the link cost change, when Y is trying to recompute, okay, the best route to X to Z, okay, particularly to X. Bellman-Ford algorithm says Y needs to try, right, calculating the total cost through neighbor X, neighbor Z. Through neighbor X, best distance from X to X is 0, trivial, but the link cost is suddenly 60, okay, just to get from Y to X. So together, total cost 60. Okay, not very good. But the other neighbor here, Z, was still under the perception that the best route is this and the cost is 5. And Y here says the link cost between Y to Z is only 1. Okay, so Y is going to insist, why don't I send packet here? Z is going to send the packet on behalf of me and taking only cost of 5 to reach X. Y does not know. Z is actually under the perception that this is the best route to go to X. So Z is going to send the packet back to Y. And Y is going to send it back to Z. Z is going to send it back to Y. So this packet here is going to loop for a while, okay, until Y discovers, okay, the real shortest path to X. So Z here, okay, being still under the impression that the best route is the one before the link change, okay, needs to know about the link change. Poison reverse is working this way. This is to help, okay, preventing bad news travel slow. In poison reverse, Y and X, okay, the two ends of a bad link, is going to tell their neighbors that, oh, all your routes, okay, all your shortest path routes to the other node along the link needs to be changed to infinite, okay. That way it prevents, okay, Y selecting Z, okay, as the shortest distance to X. And that's all the time we have for today. We'll continue to talk about poison reverse. I'm pretty sure that it's still a bit fuzzy for you how poison reverse work. So the beginning of tomorrow's lecture is going to be about an example illustrating how to use poison reverse to make sure that the convergence is going to go fast instead of counting, okay, to infinity. All right, so that's all, and go get lunch. Yeah, I know. You guys are probably still thinking, how can this be happening? Yeah. So the bottom line is very simple, okay, because the link cost goes suddenly bad. And distance vector, Bellman-Ford equation is constantly looking for a good path, a shorter distance. Therefore, this old information saying that I do know a path that is shorter in distance is going to stick around, instead of being changed. So, bad news travels slow. All right, so yeah, I'll see you tomorrow. Okay, let's see. Okay, let me leave the stream on for just a couple more minutes in case you have anything to say, anything to ask, or if you want to provide solution for quiz, I think 34 and 35. Okay, good. So let me end the stream now, and I'll see you tomorrow.